So these are the notes for section 4.3, day 1. And what we're doing is we're connecting the derivative, which is f prime, the second derivative, f double prime, with the graph of the function itself. So we're bringing into the picture in section 4.3 the second derivative. So we're going back to this question that we've been looking at all chapter. The derivative, what is it good for? And so that's going to tie into our central question here: how could derivatives be applied to make connections back to the function? So we've already talked about the first derivative being good for doing things like finding mins and maxes, finding cusps and corners. So derivative equal to 0 gets us mins and maxes. Derivative undefined gets us cusps and corners. And now what we're going to do is we're going to look at the second derivative. So if we think about this, the second derivative is the derivative of the first derivative. So, and we're going to get into that as we go through these pictures. So the first thing we're going to talk about is this term called concavity. And concavity basically gives the curve its shape. So if you notice, I've got two identical pictures here. We've got this cubic function, and this is the identical cubic function. I just made two pictures so that I can have some space to annotate on the pictures. So on this picture on the left here, we're going to look at this portion of the curve. I call this the smile. And on this picture on the right, we're going to look at the frown. So notice the derivative number line is already annotated here. In this region, we have a negative derivative. Down here, we have a derivative equal to 0. We have a min. And over here, we have a positive derivative. And then on this picture, over here, we've got a positive derivative, or an increasing function. Derivative equal to 0 here at this max, and then a negative derivative over here. So when we talk about concavity, we talk about this idea of having smiles and frowns. And so when we look at this first picture here, we can see a smile in this region and a frown in this region. Likewise over here, since it's an identical picture. So the question is when does it stop being a frown and turn into a smile? And that point is right here. And so that point really becomes important. And don't write down this, but let's talk about this for a little bit. It's where the smile starts. Okay, or we could say it's where the frown ends. So this point, it separates smiles from frowns. And so this point is so special, we give it a term. It's called the inflection point. And so that inflection point is where we transition. Where on one side of the inflection point we have a frown, on the other side we have a smile. And so I want to track the derivative here, this function, and you can see these purple tangent lines showing up here. So I'm tracking this tangent line from the min to the max, or excuse me, from the max to the min. And as we track that tangent line, it's going through that point of inflection. So if we notice, we start with a tangent of 0, and then the tangent line starts becoming negative and gets steeper and steeper. And then the tangent line needs to flatten out again, because down here it needs to be 0. So it becomes shallower and shallower and finally 0 again. So this point of inflection is where the tangent, or the first derivative, is its steepest. So it's at that location that the steepness is the greatest. And so in terms of then the first derivative, we have the steepest first derivative here. So it starts out shallow, gets steeper, 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 and then gets more and more shallow as it transitions into the next extreme point, this min here. So in this portion, we call this concave up. There's our smile. And I'm just going to put some concave up notes down here. And this shape here we call concave down. That's our frown. And so again, I put concave down, CCD here. I'm going to put some notes down here. So one thing we want to look at is the value of the derivative. We're going to look at our derivative number line here. So if we notice the derivative starts in this smile area, in this concave up profile, the derivative is negative and then goes to 0 and then goes positive. So in order to have a concave up profile or shape, in order to have a smile, we need to have a min. That kind of makes sense to you. So what is the value of the derivative doing here? It starts out negative, goes to 0, and goes to positive. So if you think about that on a number line, if we're traveling from the negative values through 0 to the positive values, those values are increasing. They're getting bigger. So we say that the value of the derivative increases when you are in the part of the function that's concave up. And so if we think about that then, and now I'm going to ask you to think about the second derivative. The second derivative is the derivative of the first derivative. So in other words, you could think of the first derivative as big F, and the second derivative of being its derivative. So that being the case, if this is increasing, then the second derivative has to be positive. Just like going back to what we were talking about last week, when the derivative is positive, the function is increasing. Well, when the second derivative is positive, then the first derivative must be increasing. And then we can kind of reverse our logic here for the concave down profile. If we look at the values of the derivative here, they're going from positive through 0 to negative. In other words, in order to have a frown, we have to have a max. And so the value of the derivative is decreasing. And if the value of the derivative is decreasing, then its derivative must be negative. That in its derivative we could call big F again, and that must be negative. So, so this brings us to then what we call the first derivative and the second derivative test. Now I'm going to leave these notes down here, and I'm going to click to the next screen. So notice the notes stayed down here. So we're going to compare these notes to our definition of concavity. So concave up, that's when we have a smile. We know that the derivative is increasing. Here's our derivative increasing. Concave down, we know that as our frown. We have a derivative that's decreasing, a derivative that's decreasing. Our concavity test then is to take the second derivative and find out where it's positive or greater than 0. That's concave up. So concave up has a positive second derivative. Concave down has a negative second derivative. In other words, it's less than 0. So that's where our test comes from. So really, our test is very similar to what we were doing last week. So let's just kind of recap last week. Last week we were talking a lot about the first derivative. We were saying that when the first derivative is positive, we had an increasing function. When the first derivative was negative, we had a decreasing function. And when the first derivative was 0, we had some special characteristics. We either had a min or a max. And we're going to kind of extend this definition, the first derivative being equal to 0. Because really what we have is a flat spot on the graph. And the maximum and the min are those flat spots. But we could also have a plateau. So if we think about x cubed, if you kind of picture what that looks like, that x cubed, I'll kind of draw it with my mouse here. It kind of looks like this, and then it goes flat at the origin, and then it continues up. So that flat part at the origin isn't a min or a max, but it has a derivative of 0. And so I call that flat spot a plateau. And we'll work more with that throughout the section here. So that's the first derivative test. Now let's extend that to the second derivative test. We're going to ask these same questions. The second derivative is positive. We know that the curve is concave up. Okay, there's our concave up. We have a smile. In other words, if the second derivative is positive, we know that somewhere along there we probably have a min. Okay. When the second derivative is negative, then the curve is concave down. So we have something like this. And when we have a second derivative equal to 0, then we must be transitioning from this condition to that condition, right? Because the only way you can transition from positive to negative, if you think about a number line again, or reverse that from negative to positive, is to go through 0. So that 0 point then is where we have that point of inflection, where we transition from a frown to a smile. So here's this x cubed shape that I was referring to on the other screen. And notice we have that flat spot right there. Okay, so that's a transition from a frown to a smile. The second derivative is going to be 0 at that location. Ironically, so is the first derivative, but we'll talk more about that a little later on in the section. So let's try to use this second derivative test. This is one way we're going to use it. This is not in the notes, but it is your notes from the last section, finding maxes and mins. And so you remember this 5-step process. And this step 1, 2, and 3 are really, if we kind of gloss over step 2 for the moment, step 1 and step 3 particularly. We're going to use this now to analyzing. We're going to kind of change the title to analyzing and sketching a function. This was the first derivative test. This one of finding the derivative, setting it equal to 0, or finding where it's undefined. Those were our critical points. Those were our mins, maxes, our cusps, corners. That was last week. But what we're going to do is we're going to stick with this 5-step process, but we're going to repeat these steps 1 and 3. And we're going to repeat that with the second derivative. So it's going to kind of look like this. We're going to find the first derivative, find our mins and maxes. And then we're going to find the second derivative, look for where it's equal to 0, and then we know our points of inflection. So we can look then to see if we have concave up or concave down if we look on either side. So for the moment, let's just look at concavity for these next 2 examples. When we do this 5-step process, we're going to have to bring another number line into the picture. We're going to have to bring in the second derivative number line. But let's start by just working with the second derivative here, just the concavity concept. Okay, so this one says prove that the function x squared, y equals x squared, is always concave up. So you know what y equals x squared is. We talk about it all the time, right? It's a parabola. So think about it. Parabola is always a smile, right? So it's always concave up. Well, let's prove it. Well, in order to prove it, we need to look at the second derivative. So what's the first derivative of y equals x squared? So take the derivative once, you get 2x. We need the second derivative though, so let's take the derivative again, and you get 2. So the value of the second derivative is 2. That's going to give that shape to that graph. It's going to give its curvature, so to speak. 2 is always a positive number. So since sometimes we call it the double derivative or the second derivative, since it's a positive number, and positive second derivative means the function is concave up, and since this is always going to be positive, because it's always going to be 2, then the function must always be concave up. And so that's just a quick, we call that the second derivative test. We just grab the second derivative and see if it's positive or negative. And then we can make that determination about concavity. So let's try this again. Let's talk about the function 3 plus sine x on 0 to 2 pi. So we know sine x looks like this. I'm going to draw it with my mouse. We know sine x looks like this. Right? Then it comes down through pi. Then it goes negative. And then it goes up back to pi. We know it looks like that. Well, what does the 3 do here? The 3 just pushes that whole thing up here. Okay? So really, the sine, we know, we could graph this already. It's going to start here. It's going to go up 1. Going to come back down through pi. Then it's going to go down to negative 1 and then come back up at 2 pi. Okay? But we're gonna work on sketching this by just working with the second derivative. So here's the function. Let's take its derivative. So its derivative is cosine x. Right? The derivative of 3 is 0. And then let's take the derivative again. So the derivative of cosine x is minus sine x. Okay? And so the first thing we want to do is set this equal to 0 and find where the concavity changes, because we know that sine graph is going to have a change in concavity. So we set that equal to 0. And when we set minus sine x equal to 0, between 2 and pi, where is the sine equal to 0? So think about the unit circle. I'm kind of drawing in space here. The unit circle sign is 0 at 0 when theta equals 0. Over here when theta equals pi. And back at the beginning again when theta equals 2 pi. So those are the points that satisfy this condition. So we know at 0 pi and 2 pi, the second derivative is 0, and that's a point of inflection. So that's going to change my smile to my frown, and vice versa. So if we come back up to here and plug these angle measures in, so let's plug in the 0 first. Sine of 0 is 0. Plus 3 is 3. So we're going to put a point right there at 0, 3. Now we're going to grab pi, put in pi here. Sine of pi is 0. 0 plus 3 is 3. So at pi, we're up here at 3. Now we're going to put 2 pi in. Sine of 2 pi is 0 plus 3 is 3. So at 2 pi, we're up there at 3, a function value of 3. Now we're going to take the concavity test. We're going to say, what is the concavity in this region? Okay, so we're going to put in pi over 2 into the second derivative, because remember the second derivative test is looking at the value of that second derivative. So the sine of pi over 2, let me draw my unit circle again in space here. Here's my unit circle. Here's 0, pi over 2 is a pi here. So the sine of pi over 2 is 1, so this whole thing is 1. But then I have a minus in front of it, so this whole answer is negative 1. That's a negative value. A negative second derivative means the original function is concave down. So I'm going to draw a frown from starting it here and ending there. Okay, so there's my frown. So notice I can draw that just by looking at the value of the second derivative. Okay, and then I'm gonna get the value of my second derivative at 3 pi over 2. So I'm going to plug in 3 pi over 2. So my unit circle here, right, here's 0, here's pi over 2, here's pi. 3 pi over 2 is down low. So the sine of 3 pi over 2 is negative 1. And then I have a negative sign out front, so that ends up being a positive 1. So this is a positive second derivative. So we are concave up. That's the shape of or the curvature of our function. So we're going to draw a smile. So we're going to start here and draw a smile. And notice when I draw a smile, I have to start by going down and coming back up again, right? So there's my smile. So here is my function then. And it's a possible value. Now, do we know this is up at 4 and down at 2? Yeah, we do, because we have a 1 out in front of the function here, out in front of the sine term of the function. So we know we have an amplitude of 1. If you didn't know that and drew this a little bit high, or drew this a little bit low, or maybe we drew this a little bit shallow, that's okay. It's just one possible sketch. And so we're going to try to increase our comfort level with drawing possible sketches. In other words, not worrying about how high the peaks are and how low the valleys are. But we'll get more comfortable with that as we go into days 2 and 3. So at this point, we can extend the graph out another 2 pi and watch the pattern repeat itself if we want to. Section 4.3, the majority of day 1 deals with the second derivative test, so you can go ahead and try working on that.